Okay, so now I think we can officially start. So this is our first lecture, and in this lecture, I'll just give you a very brief overview of what we're going to talk about in this class using some simple examples. I don't know why it's playing like this, so let me do this. Okay, so I think it's probably easier for me to control here. Okay. Is this good? Can you see the screen?
Yes.
Cool. Let me do this. Okay, so it's easier. So yeah, so I think you've seen this a lot of times, right? This is the holy grail of material science engineering. It tells you, the logical connection to different aspects of material science and engineering. So this is a so-called material tetrahedron, right? So we know that, the ultimate goal for us, by the way, can you see my mouse here?
Yeah, we can.
Okay, good. So the ultimate goal here is that we're interested in a particular performance of the material because we want to use it in certain application, like in this case, aerospace engineering, right? But in order for this material to achieve this performance, for example, high resistance to fatigue, in high temperature and high pressure environment, right? In order to achieve this performance, we have to know that, what are the required properties of material, right? If you're interested in applying this material in the aerospace application, you want the material to be very strong, for example, have a large fracture strength, good ductility, etc. But the way to engineer the property of the materials, ultimately goes back to the structure, right? How can you control the size of the grains? How can you put in the right number of dislocations so that you can have a optimal combination of both strength and ductility, etc. But the structure of material is then determined by how you make the material, right? If you cast the material at different temperature, you cool the material in different cooling rate, you're going to end up with different microstructures, different size of the grains, etc. So all these aspects of material science engineering, namely the structure, the properties and performance, and processing, they're all interconnected, right? So this whole tetrahedra is basically the key elements of material science engineering that we're studying and we're interested in. Okay, so, and also we know for a fact that the microstructure of material, which is, I think, the majority attention of current or modern material research has been focusing on, is a very complex subject, right? The material microstructure is not just on a single length scale, right? It's actually, the material properties are not only depend on a single feature of the microstructure, it's actually depend on features on different levels of microstructure, right? So this is the macro level that we've seen every day. We're interested in, knowing the stress distribution of this airplane when it's in service. And this color map shows you, for example, the stress, roughly speaking, the stress of different parts of the airplane. But we want to know and we want to make sure that during the service, these rest spots are going to be safe, right? After how many times of usage, we still want the material to be reliable. And those, the performance of these material determined first by the grain microstructure. Okay, so this is the simulated microstructure of a titanium alloy, and you can see that they have some primary alpha grains, these large polyhedral things, and very small the anisotropic beta grains that come from the solid-solid phase transformation. So the microstructure of this, like the size of the grain, how they're oriented in this microstructure, they're all going to play a role in determining the mechanical properties. But if we further interested in, okay, how a possible crack going to initiate, or how a particular part of the material gonna first yield into plastic behavior, we have to go to a smaller scale and worry about dislocations and their interactions, right? But if all the way eventually, the ultimate properties of material are determined by this atomic scale thing. So, all these complex length scales of microstructure features all together, give you the performance of the material. And every single phenomenon you see in the material behavior, for example, the fatigue initiation, the crack initiation, or things like that, going to go all the way starting from atomic level and propagate up until that we can see this crack in the macro scale. So it's very important for us to really have a good understanding of the microstructure of material, and especially, when you make the material, what are the processing conditions, that can affect different aspects of microstructure and how you control them, right? So this is a really important topic in material science engineering, and that motivates our class. In this class, we talk about phase transformation. And why is that? Why this is important? Because in material processing, we're ultimately dealing with phase transformations. Okay, so here I give you another example. Let me try to show this. I think I have some very nice animations. So basically, based on what we discussed, right? So in this class, we'll mainly focus on the microstructure evolution part of material, and this is related to the processing. Okay, so the example I give you here is the animation of the selective laser sintering processes. So you can see that this blue thing is a densely packed powder of some pre-alloyed metal, maybe aluminum or titanium, right? So traditionally, when people make a material, they typically melt everything and pour the hot melt into a mold and wait this hot melt to cool down so you can have particular shape, and you polish these parts and then into the shape you want, and that way how they make it. But recently, people have developed this very advanced technique called additive manufacturing. So you don't have to really melt down everything. You can start with a solid state, and you just, in this case, use laser to locally melt or locally sinter the material in a solid state. And in this case, you can save a lot of energy and you can save a lot of material, right? Because in this case, you don't have to melt down everything. You just locally need to heat up the local material, make sure they form tight bonds together. And then you just you can directly make the shape of the shape you want by designing the path of the laser. Okay, so that's a very cool way. And during this processes, after you make the material together, because you heat up the material in certain type of way, either make it into liquid or just heat up and then cool it down, right? So this means that the material can undergo a different type of thermal circle, and this will typically introduce a phase transformation in the material. Like in this case, in this laser sintering processes, initially you start with a material with very large grains, like these material. This is the microstructure after laser sintering, but before the sintering, you do not see these very fine beta grains in these directions. Everything gonna be like homogeneous large alpha grains. But when you heat it up and cool it down, these beta grains begins to grow as a solid transformation in the material system. So that's going to change the microstructure, right? So the whole material after you make the material into certain in a particular shape, the mechanical performance you measure will be different than the pre-alloyed powder because they have a different microstructure. Okay, so all of these are related, and the key thing that we're interested in is that how this particular processing, how you heat up the material and cool it down, can affect this microstructure, right? So how the microstructure properties like the grain size, the volume, the grain orientations are related to these processing parameters, including cooling rates, like aging temperature, laser powder density, and spot size, and etc. Okay, because these are eventually going to determine the mechanical properties of the material system. Okay, so that's basically what are people doing in modern processing. Now, why this is important, because once you know this connection, you can do material design, right? Once you know that how you're processing going to change the microstructure, and you know that what properties can be achieved by different microstructure, and then you can design or develop a set of optimal processing conditions that achieve, so that you can achieve a microstructure material with desirable microstructure for a particular set of mechanical properties or other properties you want for the particular application, right? So this is basically now how we do material science and engineering. And you can see from this feedback loop that a key thing is you have to know what happens during the processing, right? When you heat up the material and cool it down, what's going to happen in the microstructure. Okay, and as we said before, the key things happening in the microstructure is different type of phase transformations, right? You can have large alpha grains, and then if you heat it up and cool it down, you can induce the growth of a secondary phase, like a beta grains within the alpha grain. How it grows, how fast it grows, how large it can grow, how these are related to the processing temperature, etc. And this is important. So that's going to be the main topic of our class. Now, of course, what we're going to discuss in this class will not be so advanced in these applications, because for system as complex as this, I don't think the simple mathematical tools we introduce in this class can be directly applied. Okay, in most cases, you have to use very delicate experiments or computer simulations to really get insights into these complex systems. But nonetheless, the fundamental principles that we discuss in this class will be extremely helpful to understand all of this, to understand what's happening in the system. We cannot make quantitative predictions using the theories we discuss in this class, but we can definitely make qualitative predictions. We can rationale what we're going to see in these systems. Okay, so that's going to be the motivation. That's basically the motivation of this particular class. Why we're still studying, these theories that people developed over 50 years ago, like in the middle of last century. Well, because they're still very classic, theories that can provide a lot of insights on what's happening in more complex systems. Okay, they cannot directly provide quantitative predictions, but they can still give us a very good intuition going to happen in a material system under different processing condition. Okay, so that's basically the motivation. Any questions up to this point? Okay, so if not, let me continue. So this is like a more detailed wheel of this particular laser sintering processing. Okay, I think it's just cool to give you some idea of the most current processing technology that we have developed. Again, this is basically showing the simulation of the temperature field as you move the laser spot, around the system. In here, this is just we're just trying to sinter a rectangular a plate from the powder pack. Okay, the reason why we do this is because it's easy to implement in the simulation, but in principle, you can actually do much complex shape. Okay, so here is what's going on in the microstructure. Okay, you can see that initially you start with these predefined alpha grains. I think it simulates. This is a GF. Yes, you start with these alpha grains, and you can see that the small dark beta grains start to form or nucleate along the grain boundaries, and then the start to grow in a very anisotropic way, and eventually they take most part of the alpha grains, but you still have some of the original alpha phase left on the grain boundary probably and within the middle of the alpha grain. Okay, so these very fine structures and these massive grain boundaries between these beta grains will significantly change the properties of material. We're going to make this alloy very, very stiff, very strong, but on the other hand, it's going to reduce ductility compared to the original material where we have these very large grains. Okay, we're going to talk about the solid-solid transformations probably in the later half of this class after the midterm exam. Okay, so to understand these more complex systems, we need to understand the fundamental principles behind this, and we're going to use simpler, much easier transformations like in liquid-solid transformation to illustrate those principles and how we should apply them to this more complex system. Okay, so that's the example. So I hope this motivates you enough for this class. Okay, so this is very interesting and exciting class that we're gonna have. Okay, so now I'd like to introduce some fundamental concepts. Okay, so because we talk about phase transformation, so the first thing we have to clarify is what is, or at least what do we mean by a phase, okay, in this class. Now, I don't think there's a formal definition for a phase, but this is a typical definition we use in material science engineering. And it basically reads like this. A phase is basically a region within the material system that have a unique structure and or composition different from other regions in the system, such that this particular region or this phase is going to possess a distinct set of properties, okay, from other regions. So this is a very formal definition. Okay, I don't think it's going to be very useful to us. So we're going to use some examples to understand this. Now, this is the part that I would expect some class activities and participation from you guys. I understand this might be difficult because we're using the Zoom version, but still, I want basically to make sure that we're on the same paging. So I want to get some feedback from all of you, okay, if possible. So now here I give you two examples, right? Clearly, now the left part, this is just a cup of water. Let me see where's the mouse. This is a cup of water, right? We just focus on the water, forget about the glass and the cup. Let's just focus on the water. How many phases or how many faces do you think there are in this system, in this cup of water?
One.
There's one phase, right? The clear to everyone, just have a water is a homogeneous phase. Why there's only one phase? If you apply this definition to the system, what makes you think that, or make you come to the conclusion that we have only one phase?
Homogeneous throughout with respect to structure.
Same properties throughout.
Okay, so if we look at this definition, right, there are a couple of, let me see, this is this. Okay, so there are a couple of key elements that we can extract from this. Number one is that, okay, this, if you have a phase, right, this phase either going to have a unique structure or composition, right, different from other regions, right? This is one thing. And this uniqueness of structure and composition going to be manifested in forms of distinct properties, right? So basically this definition tells us that, okay, if you want to distinguish different phases in the system, there are a number of things you can try. The first one is that, okay, if this material or this system contains multiple regions that have different properties, okay, if not, probably they're all, there's just a single phase, right? Or if you want to be more specific, if you have some tools that allows you to look at the microstructure of the material or study the composition of the material, and then you can see, okay, whether in this material, are there any regions have different composition or microstructures than the other region? If not, then this is probably just a single phase system, right? So this is basically based on the definition. Now, if we go back to this system and we look at here, okay, of course, we cannot see the microstructure. We cannot see the composition, or probably we can because I told you this is water, right? So we know that this system is water is made of H2O everywhere, and also is a liquid. So it's the properties and the structures is homogeneous and uniform everywhere. So we know this is a single phase system, right? And this is quite compatible or consistent with our intuition of understanding of liquid water, okay? But again, we see how we apply. We applied the definition. Yes. Any questions?
Yeah, I have a question.
Sure.
So if you consider the surface of the water, only surface of the water, so the arrangement of the atoms on the surface will be different due to the surface tension, right?
Yes,
From
but that's a good question. So with this again, so this is a very good question. So first, when we talk about the phase, we focus on the bulk, and also in terms of the surface, usually we do not call that a separate phase. Okay, so if you talk about the surface, we're talking about a two-phase interface between this vapor or gas and this liquid. Okay, so we do not call the surface a separate phase. We typically call that a surface, and we'll go back to this point later. But if you just to focus on the bulk within, the cup in the bulk water, that is a homogeneous single phase. But this is a very good question, because surface will also play a very important role in our subsequent analysis. Okay. But so if we ignore the surface, ignore the surface between the gas and the surface between the glass, just to focus on the bulk of the water, we can safely say it's a single homogeneous phase. Okay, so that's our conclusion, which is, thank you very much for the question. This is good. Okay, so that's that. Okay, so now how about this system? So this is a iced water. Okay, we just have experience every day with this guy. How many phases do we have in this system, and why?
Two phases.
There are two phases, obviously, right? So this is, based on our intuition, we know ice and water are two different phases. Okay, so when we put them together at 0 degrees Celsius, we know they coexist with one another. Okay, by coexist, we mean that if you keep the system at this temperature, water will not freeze into ice and ice will not melt into water. It's just going to keep the same amount forever if we can keep the system stable at that temperature. Okay, so now why, this is our intuition, but if based on the definition, why do you say that we have two phases here?
It's structurally different.
Okay, the structure is different. Okay.
Even
so
the properties are different.
the properties are different, right? How about the composition? Are the composition different?
The composition is same.
Composition is the same. Arrangement is different.
Exactly.
The refractive index and the things like that.
Yes, exactly. So that's exactly the right way. So now if we want to analyze this in a rigorous way, the first thing we see is, again, we can see the microstructure, right? If I do not give you any, X-ray data, you just look at ice and water, we can see microstructure. But what we can see here, or what we can observe here, is the macroscopic property, right? We know the ice, if you hold the ice in your hand, what is the mechanical property? What do you feel? It has a resistance to shear, right? It cannot deform easily. You have to apply force, and then it can deform very tiny, very, very slightly. So we know this guy has a non-zero modulus response to shear forces, right? How about liquid water? Does that liquid water have this rigidity?
So yeah, it has less viscosity as compared to ice.
Yeah, it has no rigidity, but it has viscosity, right? But very small viscosity, but no mechanical rigidity, no modulus. So this basically tells us, okay, these two things, which are made of the same H2O molecules, have distinct mechanical properties, right? So, and this basically, okay, can, based on this and our definition, we can probably say, okay, at least these two are different phases distinguished by their mechanical properties, right? But if they have this manifestation of distinction in their mechanical properties, typically they're going to have a difference either in the microstructure and or the composition. And as we said before, both of these systems are made of H2O molecules, so there will be no difference in their composition. So the only difference that's going to cause this manifestation of their distinct mechanical property will be from the distinct microstructure. Okay, so that's basically what we learned from this example, which I think is very helpful. This is consistent with our intuition, but I think there's much deeper science behind this. Now, let's go to the next slides. Okay, why it doesn't work? I apologize for these tech issues because this is the first time that I'm using Zoom to teach. I just came back from a long sabbatical leave. So let me see. Yes. Okay, so why I still have these things?
Professor, you should be seeing a clear option there at the annotate bar.
Okay, so this one, and I do clear, right? Is this clear all drawings? Okay, thank you so much. Okay, so yes, so that's, let me then, I'm sorry. So how can I go back to the previous slides? Let me see. Apologize for this. Let me do this. Yes. Okay. So yes. So this is about the phase, right? So I think now we have a good understanding of the phase. And the next thing that we're interested in. Okay. Yeah. This is the microstructure, right? So yes. So as we from this analysis of this example, we know that these two phases, ice and water, or in other words, liquid and solid, are distinguished by their mechanical property and the microstructure, right? And now if I give you these two very schematic plot of the microstructure and tells you one of them is associated with liquid water and the other one is associated with solid ice, which one do you think is associated with water and which one is associated with ice?
Lower one is liquid and upper one is ice.
Okay, so lower one with liquid and upper one with ice, right? Is that clear to everyone? And why? Why can you make that conclusion?
Because in the upper one, I can see the periodic arrangement of the molecule. So it's quite like the arrangement is regular and periodic. So, and in the lower image, the arrangement is the distribution of molecules is random. So
okay. Okay, so this is a very good point. So basically, this example gives us a very, a general picture of the distinction of microstructure from a liquid and a solid, right? In general, right? So, in general, if you look at the atomic level microstructure of a liquid, typically you see a disordered microstructure like that. Okay, so first we need to understand this is just a snapshot. Okay, it's not, the real microstructure. The real microstructure is that these atoms are moving all the time in a crazy way. This is, they always have these thermal motions and they constantly change positions, they collide with one another. They may have some, strong, in this case, hydrogen bonding between the, have a snapshot here, but even in the snapshot, it has a disordered nature, right? You don't see any clear pattern of packing of these atoms into any ordered fashion. Okay, you see some local arrangement, but still you don't see any global order or periodicity in the system, right? So this is our, intuition or basic principle of a liquid structure of the atomic level. But if you look at the solid structure, okay, in most materials, at least in this particular class, when we talk about solid, we're referring to a crystalline microstructure. Okay, you see the atoms or molecules that are packed in a periodic structure. And because of this ordered arrangement of the atoms, they can really rearrange themselves, organize themselves so that they can find the right position to form very strong chemical bonding between the neighboring atoms. Okay. And this actually gives rise to the mechanical rigidity you see in the solid compared to the liquid. Okay, in the liquid, you still have interactions between these building blocks, but there's no permanent strong bonding between the neighbor atoms. So that's why when you apply a shear force, eventually you can see that the liquid is going to flow. Okay, so that's the distinction in the microstructure. Okay, again, it's a more fundamental way to distinguish different phases, and this distinction in the structure is manifested in terms of the mechanical properties. Okay, so that's what we want to say about this particular example. Okay, so now we understand what is a phase, right? Now let's try to use the example to see what is a phase transition. Okay, so now again, let's use our intuition. So if I start with a cup of water, right? And then how can I make this cup of water into ice water or pure ice?
Cooling it.
There are different ways, right? The easiest one, or the one that we have, a lot of intuition, is that we just put this water in the refrigerator and patiently wait for some time, and then we can see what the ice grow out from the water, right? So this processes that a single phase under certain thermodynamic conditions that transform into a different phase. This is roughly speaking called a phase transformation. Okay, so and that phase transformation or different phases are very conveniently, I would now see, maybe characterized or described by the so-called phase diagram. Okay, so in here I show this very simple example of a phase diagram for the water system, okay, or for the H2O system more precisely. And you can see that for this very simple molar, I would say, homogeneous system, okay, we only have one species, right? There's not a alloy, there's only one molecule, H2O, in the system. So it's a homogeneous single component system. We only have three distinct phases, right? And we talk about the water phase, which we're very familiar with and very important to our daily life. We talk about the solid phase, which is ice, okay? And there's a vapor phase, okay, which occur at low pressure and high temperature. This in thermodynamics and other like chemical engineering applications, the vapor or the gas phase is very important. But in the material science engineering, we are mainly focused or interested in the water or the liquid phase and the solid phase, because that's the two state the material science engineers that we deal with most times, right? We deal with solid materials, and sometimes we melt them down to process the material in the liquid form, but we rarely deal with vapor. But now this is I'm thinking in the traditional way of structural alloy and things like that. But I know that there are more advanced techniques such as vapor deposition for semiconductor processing, things like that. But that again is not the main focus of this class. We're in this class mainly focus on the liquid and solid phase. Okay. And so, as we said before, if we want to convert this liquid phase into ice, right? One thing we can do is to go across this temperature axis, okay, this horizontal axis temperature, right, by cool the system from a high temperature to a low temperature, okay. But if you look at the phase diagram, okay, this horizontal axis is the temperature, the vertical axis is the pressure, okay. There's another way that you can introduce a phase transformation, although this is probably more difficult because the slope of this phase boundary line, right, is to you apply pressure, okay, to the system, well, keep the system at a fixed temperature. Okay, there's another way that you can achieve that. But as you can roughly see from this phase diagram, it's much difficult to achieve that pathway. And also there is a certain limit on the temperature that you can actually apply that, right? So there's no way for you to achieve any liquid to solid transformation by increasing pressure, okay, when it's actually, when the temperature is beyond this critical point. Okay, but anyway, and in this class, our main focus is achieve phase transformations through this temperature pathway. Okay, because that is the way how we process a material system. Okay, in most of the cases, what we do in the processing is that we do not change the pressure. The pressure will be kept at atmosphere pressure, and we change the temperature. we cool the system in different way, either fast or very slowly, so that we can introduce the liquid solid transformation at different rates to achieve different microstructure. Okay, so that's basically the phase transformation and how we can induce phase transformation in the material system of interest. Okay, so so now, because we use the phase transformation, to make material, to make solid material, to process solid material, and we know that during the phase transformation, the microstructure can undergo a dramatic change, right? Like in this water-ice transformation, what are the changes of the microstructure? I think we already illustrated this, right? So in the liquid form, the water has a very disordered microstructure. The molecules are just moving around randomly, but in the ice, in the solid form, they're magically packed in a very nice a network structure, right? So give you a lot of interesting properties. So this is an example of the change of microstructure during the transformation, right? And we know that if you have an alloy instead of just a simple, homogeneous, water system, the change of microstructure will be much more complicated. And the change of microstructure also going to occur on a multiple length scales. Okay, so it's very important for us to understand this change. Okay, but to understand this change, basically we have to understand this phase transformation. Okay, so here at least the two most important questions of interest here. Okay, so if we want to study phase transformation, we have to answer this question. There's no way to around this. Now, the first question is that why the transformation occurs. Okay, why the transformation occurs. And the second question is that how the transformation occurs. Okay, so you will find out that through this entire semester, we will just be answering these two fundamental questions, but in different transformation pathways. Okay, we're going to start with the very straightforward water-ice example, and eventually we're going to study different type of phase transformations in alloys, but we're always asking these two fundamental questions: why the transformation occur and how the transformation occur, right? Because if we know why it occurs, we can actually induce proper condition to make them occur. If we understand how they occur, we can control the conditions and control the transformation so that we can engineer the microstructure. Okay, that these make sense?
Yeah. So I have a fundamental question about the phase diagram actually.
Yeah.
So when we increase the pressure, actually, so we should expect the freezing point of water to be increased, right? So why it's getting decreased?
I'm sorry, the question that is if you increase the pressure.
Yeah, so we should expect the freezing point of water to be increased, right?
No, because the pressure, so basically increasing pressure and decreasing temperature, they all facilitate the transformation into the liquid, into the solid, right?
Yeah, but means
so yes, so basically it means that, so if you had at high pressure, oh, you mean that you have, if you had a high pressure, the freezing point should be higher? Is this what we're talking about? No. This is because the most systems, this is the case. But water has a very, very peculiar behavior, is because this structure. Okay, so so this is a good point, but in most of the case, because this is a critical point, because if you look at microstructure of water and ice, and if I ask you, what do you think of the density of solid ice compared to liquid water? What is your question? What is your answer? Which one have a higher density?
The liquid water.
The liquid water have a higher density, right? So this is a peculiar part of this particular system. If you have a normal, like argon, very simple atomic, substance, and what you said is totally true. But in terms of the water, because when water freezes into this solid form, it actually forms an open network structure. Okay, so the density of this system actually decrease. So if you compress the system, it's actually gonna suppress the crystallization, because it's more difficult for them to form into this open structure because you crash them, right? So that's why. But for other systems, for normal liquid solid transformation, like in simple argon, the trend will definitely, as this line gonna go as what you see will be like this. Okay, but for the water is with.
Can the same thing be true regarding the bismuth? Because bismuth also shows anomalous behavior, like solid bismuth is having less density than liquid bismuth.
I didn't see the phase diagram, but I would say it's probably yes, if the mechanism is the same, but I cannot exclude other mechanisms for that system.
Thank you.
Very good question. Okay, so yes, so that's basically motivate. So basically, these are the two key questions that we always bear in mind when we talk about all the other transformations. Okay, so now I would like to ask you these two questions for the ice and water system, because we're quite familiar with this, right? Now, why do you think that if we cool the system, if we start with a liquid water, but we now cool the system by lowering the temperature, why water transform into ice?
Yeah, the Gibbs free energy of phase transition from water to ice is negative at lower temperature or 0 or below 0 degrees.
Okay, so basically, this to answer this question, we're basically asking a more fundamental question: is that what actually determines the stability of a phase, right? What determines the stability of a phase under a given set of thermodynamic conditions, right? What does this mean is that, okay, if I give you a set of pressure, I give a set of temperature, I ask you to compare. Okay, I have two candidate phase, water versus ice. At this given set of thermodynamic condition, which one is more stable, right? So because that's basically why the transformation is going to occur, right? Now, if water is more stable, it's going to remain as water in this form and this condition. But if ice is more stable, so we're going to see a transformation from water into ice, right? So to answer this question, basically we're asking what is the criteria to determine the thermodynamic stability of a system in a particular phase for a given under a given thermodynamic condition. Okay, now what is that criteria? So I think we already get this answer right from the answer. So that is the thermodynamic energy or state function of the system. And in this particular system, because we're talking about pressure and temperature, using these two as my thermodynamic condition, so the correct energy functional we should look at is the so-called Gibbs free energy. Now, for those of you who do not know this term, it's okay. We're going to talk about those later. But generally speaking, okay, I'm not really expecting to get to Gibbs free energy at this point. I think this is very great. I just want to get energy as a criteria, okay, for the stability. Because based on our intuition, for whatever system, if you have a lower energy, it will be more stable, right? A lower energy is always favored by nature. So that's basically what we want to get here, okay? So to understand why the transformation occur, okay, we really need to dive into the thermodynamics of the system, okay, and work out the proper energy functional that are the criteria or determine the stability of each phase for a given set of thermodynamic conditions, right? So that's basically, in order to answer why they occur. So that's why we need to, spend a few lectures on thermodynamics to address these. And now the question is that how this transformation occurred. I think this one is even more difficult question. Okay, so we now know that, okay, so if I cool the system to, at atmosphere pressure to a temperature lower than 0 degrees Celsius, the water is not stable. It wants to transform into ice, right? Because ice will eventually have a lower free energy than water in this condition. But how the water going to transform into ice?
It starts crystallizing at the nucleation point.
Structural rearrangement.
Some intermediates or something like intermediate phases or something driven by kinetics of the phase transition.
Exactly.
Diffusion also.
Yes. All of these are the key aspects that going to determine how this is going to occur, right? So, we know that based on our experience. So first, I want to say that there are different pathways that how transformation occur. But based on our data experience, we know that this transformation do not occur, suddenly, right? It's not that you have this cup of water and then suddenly everything just immediately turn into ice. You see this in the friction, these movies, but in reality, you hardly see this pathway occur. The most, commonly pathway how water transforms into ice is that, if you put this water into refrigerator, and if your refrigerator have a transparent glass that, wall that allow you to observe this, and if you're patient enough to see what's happening, you probably first see that there's small ice things grow from the wall of the glass and maybe on the surface of the water, right? And these small ice crystals start to further grow, into the bulk liquid, and eventually everything just turns into a solid ice. Does this make sense to everyone? So this is very intuitive, right? I think I have a movie for you for this, but I'll show you later. So, so we know that this is from the macroscopic observation. We know that you have to form a small amount of ice, and we could call this a nucleation processes. And then this amount of ice have to grow, right? And then eventually going to occupy the entire system, and your water transform into ice. So now, based on this thought experiments, or this very familiar observation, virtual observation, that we know that. Okay, so the transformation at least should contain two processes. The first one is nucleation, and the second one is growth, right? But what determines the nucleation, and then what determines the growth? Or what mechanism or what processes that play the most important role in these two different key steps in the phase transformation processes?
Again,
Okay, so
Temperature difference.
the temperature difference is going to be the thermodynamic driving force. But now we're talking about, what's happening here. Think about the atoms, how the atoms are going to rearrange themselves, what the atoms are doing, what the molecules are doing in this process.
Surface energy of the solid surface on which the nucleation is being taken place.
Okay, so let's make it clear. This is where we're going to spend most of the time on, because I think it's less obvious, right? So first, let's focus on the nucleation processes. Okay, what do you think happened during the nucleation on the atomic level?
Diffusion.
Essence of different atoms, they have to come together first.
Okay, so let's think about this. Okay, what is the consequence of nucleation? Let's start with ideal system where you have a pure liquid and there's no nucleus at all, right? What happens after nucleation? What do you see on the atomic level? Think about the nucleus is very small.
Yes, so the atoms of the liquid are adsorbed on the surface of the solid. So in a film like
initially, suppose there's no solid at all. There's all liquid, and we think about the atomic picture. So all the atoms are just randomly moved around and have this disordered nature. And then what happens after nucleation?
Atoms get ordered within the liquid.
So after the nucleation, you suddenly find a small region, very tiny small region, such that in this very small region, all the molecules or atoms are magically packed themselves in a very ordered way, like you find in a solid. Does this make sense?
Yeah.
This is very important. Okay, on the atomic level, what you see is that before the nucleation, right, everything is just random. You have these atoms moving around randomly. You have this, this very homogeneous pack with no order. But suddenly after nucleation, you find that the atoms, they arrange in a very small, tiny region. The atoms arrange themselves in a periodic way. Okay, in a very ordered way, as you find in the liquid. I'm sorry, in a pure crystal. Does this make sense to everyone?
Yes.
This is very
So I
important.
have a question here. So if the nucleation occurs in the glass, so if I have glass which is having amorphous structure.
Yes.
I take copper or crystalline material as a container. So the process of the nucleation and the structure of the ice will be different a little bit, or?
No, you mean the glass? You mean the nucleation on the small ice form on the wall of the glass, right? You're asking if this has no. So in this case, no, it wouldn't have a different microstructure, because if you crystallize into everything crystallized into this crystal form of solids, it will eventually have the same crystalline microstructure, but it may have different orientation of your axis, okay? But it will have the same crystalline microstructure, but it will have different orientation. So we're going to have a polycrystalline ice, okay? But now let's talk about homogeneous nucleation. Let's talk about, the system is very large. We do not care about what happens on the boundary. We just care about what happens in the bulk liquid, right? And then basically this means that if you have a nucleus, it means that there's a very small region of the liquid. In this region, the atoms magically pack as if you were found this in a perfect crystal. That is what atomic level process of nucleation. Does this make sense to everyone?
Yeah.
Okay, so yes.
Once the nucleation starts, can it go back to the liquid phase?
Exactly. This is the question I'm going to ask you. Okay, so now if we look at the water, okay, so say I prepare water at 5 degrees Celsius. Okay, is that clear? So this is just the water, but it's cool water that I can drink. Do you think that in this water, if we look very carefully, we can find small regions of ice? Or in other words, in this water, do you think that all of the atoms are going to have this totally random arrangement, or there occasionally will be small region of atoms that arrange themselves spontaneously into a microstructure of ice crystal. And this is a water, macroscopically, this is a cup of water at 5 degrees Celsius. What would be the answer? Do you think you can find small ice, very tiny small ice in a water that at 5 degrees Celsius?
Well,
Probably
depend
at
on
this.
I don't think the ice will be there, but ice-like liquid water can be there. Like means not that much ordered, but a little bit ordered, like more ordered
No.
than water at 25 degrees.
No. Let's talk about this. We're talking about atomic level things. Maybe ice is not a good word to use. Let's talk about this atomic level arrangement. Do you think you can find this, ice crystal-like atomic level arrangement in what we call liquid water at 5 degrees Celsius?
It's less likely.
Yes.
Less likely, but you can still
Yes.
find them, right? We cannot
do
see
find
them. We do find them, but we cannot see them because they're so small, right? But we know they are there. But do you think these things are going to be stable? They can be there for a long time, or they just be there for a tiny second, or tiny of 1 millionth of second, and then they just melt back.
They will disintegrate back into their stable form at that
They'll melt, right, with quotation marks. They'll melt back into the liquid structure, right, into the amorphous arrangement of atoms. Does this make sense to everyone?
Yeah.
Okay, so now what do we call these processes? What do we call the process that, okay, you have initially a totally random region, and then suddenly in this region you can find a small, but not stable, but yet still with a finite time of existence of a ice-like structure, and then this structure goes back to the liquid structure. What do you call these processes?
Transition state.
Yes, that's not exactly true, because transition is metastable. In this case, they're so small we cannot call this a state. We call this process. We call this fluctuations. That makes sense? We call these fluctuations. Okay, is this a word that's familiar or makes sense to everyone? Because you constantly the system have fluctuations, right? We know that small ice are not stable, but you're still gonna see them, right? Because locally you may still have regions that form into the small ice. It's simply because thermally they're unfavored, so they're not stable, but still you have these fluctuations. That makes sense to everyone? And the key thing here is that these fluctuations, they exist at all temperature. Okay, even at temperature higher than 0 degrees Celsius, even in a system that you would call this liquid water, if you look carefully, you will see these things. So they're there. These small fluctuations or these ice nucleus, they're always there in the water. Does this make sense to everyone? Okay, I know this is a little counterintuitive, that is what's happening. Okay, so now if we keep this in mind, keep in mind that it doesn't really matter what temperature you have or what is the macroscopic phase you observe. In the liquid water at temperature higher than the freezing point, you always gonna see, although very temporarily, these ice nucleus, right? Now, what happens or what's gonna happen to this ice nucleus when you cool the system below the freezing point?
Yeah, so then it favors the solidification.
So, at temperature higher than the freezing point, we know that these ice nucleus or these small ice-like crystals, they're not stable, right? Because temperature is so high and they're easily melt back into the solid, the liquid structure. That makes sense to everyone? These things are not stable, they're gonna melt back. But what happened if I cool the system such that these things or these small nucleus are now become favorable? Because if I cool the system below 0 degrees Celsius, we know that this structure now is more favored in terms of their free energy. So they can become stable compared to this other structure. So what's going to happen? Do you think these guys, small crystals, going to melt back?
No.
Or they're going to keep on growing?
They are going to keep on growing.
They're going to keep on growing because they're more favored, right? They want to grow larger because this is going to further decrease the free energy of the system. Does this make sense to everyone?
Yeah.
Okay, so that basically answers the question how the transformation occurs. Does this make sense? the transformation occurs through nucleation and growth, right? How the nucleation occurs is through fluctuations, because it always have these small nucleus in the system, even you're in this liquid state. But why, if you cool the system below the freezing point, it begins to grow, is because these small nucleus becomes thermodynamically stable, right? And then there are more and more atoms adding on to this small nucleus. And when the add-ons to the small nucleus, they transport to the surface of the nucleus through diffusion, and they rearrange themselves in an ordered way, so that the whole thing, the whole small crystal begins to grow larger and larger, which is further favored, because if you have a larger solid, the system's free energy can get lower. Does that make sense? So this basically, once we understand this picture, although it's very qualitative here, but this is the most essential, the essential components of the phase transformation, right? We ask why it occurs. We know that, the ice is more favored at lower temperature because thermodynamics tells us, the ice have a lower free energy. So it's favored by nature. So that basically we're going to see water eventually transform into ice. How water transform into ice? Well, it's going to utilize the fluctuations to form small nucleus. And at a lower temperature, these small nucleus are stable. So there will be more water molecules adding on to this small nucleus, pack themselves in the crystalline structure and grow. And eventually the whole water transform into ice. Does this whole picture make sense to everyone? Okay, so that basically covers what we're going to discuss for the first half of the semester. Okay, very qualitatively. So now what we're going to discuss for the rest of the first half of the semester before the midterm exam is to make all we discussed here more quantitative. Okay, we're going to introduce, we'll see in what the detailed mathematical form of the thermodynamic free energy functions, how it is related to the microstructure or the composition of different material, and how the atoms are transformed, or what are the mathematical way to quantify the transport of different atoms, molecules to the surface, and how they attach them and how it grows. Okay, we just make this more quantitative, but intuitively we already discussed what we need to discuss for the first half of the semester. Are we clear on this? Okay, so now after that, I think this is a quick summary. Okay, again, this is ice and water, the difference. And one thing that I want to point out is that we talk about the energy of the system, right? So we here need to be very careful about what energy we talk about. Okay, so now there are different forms of energy for a system, and we're going to discuss this in more detail in the next lecture. So don't worry that if you do not get it right now. So if you look at ice and water, we understand or appreciate that these two things have different microstructure, right? Ice had this more ordered way of packing, and water have this disordered way of arrangement of the atoms. Now, if we're thinking about that, okay, so the majority of interaction energy, okay, if we talk about energy, let's first talk about this internal energy or interaction energy or potential energy of the system. Forget about their kinetic energy, just talk about their interaction energy. And by interaction energy, what I mean is that now if this water molecule form a hydrogen bonding with the neighbor water molecule, this hydrogen bonding is actually a very favored configuration and going to reduce the energy of the system, right? And if you want to break this hydrogen bond, you have to apply a force or do work, which means that you're going to increase the energy of the system, right? So by interaction energy, I simply mean the energy associated with the chemical bonding between the building block in the system. Okay, does this make sense? Okay, this is roughly speaking, okay, but this is our setup. So now in this case, what do you think if you compare this ordered packing of water molecule to this disordered packing of water molecule, in this ordered packing you have a lot of nicely formed hydrogen bonding, where in this case you just have some occasionally hydrogen bonding formed between near neighbors. If you compare these two microstructure, which one do you think is going to have a lower interaction energy, and why?
Okay, sir, can you repeat the question?
Okay, so we're talking about interaction energy, okay, because we already introduced energy going to play a role here, right? So I'm asking that, okay, if we understand the interaction energy as energy associated with the chemical bonding, in this case, the hydrogen bonding, right, in water, okay? If I ask you to compare, okay, here we have this very ordered packing of the system in the solid form. And here we have this disordered arrangement of molecules in the liquid, okay? With our definition of interaction energy in mind, which state, okay, this solid state or liquid state, which state or what microstructure gonna give you a lower interaction energy of the system?
The solid will have
Solid one, ice.
Solid one, ice.
Okay, I think I should open a pool for this, but anyway, so the question is that which one gonna have a lower interaction energy, right? And because we already say the interaction energy is determined by what? It's determined by the hydrogen bonding, right? Because hydrogen bonding is going to give you negative energy because it's going to reduce the energy of the system.
Yeah.
So the more hydrogen bonding you have, the lower of the interaction energy is.
Yeah.
Does this make sense for everyone?
Yeah.
Okay, so now if you compare the liquid versus solid microstructure, which one you can expect to see more hydrogen bonding?
Solid.
The solid one, because it has an ordered microstructure, right? And every single atom or molecule going to have hydrogen bonding with neighboring atoms in an ordered way. So you have much larger number of hydrogen bonding in the solid form compared to the liquid. So this solid will have a much lower interaction energy, right? Okay, that makes sense to everyone? Okay, so now okay, so now the question for, I supposed to ask you, or I plan to ask you is that, okay, if we say, okay, energy determines the state of the system, and we already from our analysis show that the solid will always have a lower energy, right? Why liquid can ever be favored by nature as a stable phase?
because entropy, higher entropy is more favored.
Okay, because the question is that, okay, so this is a right answer, but so the question is that, okay, if we consider energy is a key criteria to determine stability, right? And based on our analysis, we know that the solid phase have a lower interaction energy, right? And why liquid can still be favored at certain temperature. So
because a higher temperature favors the forming and breaking of bonds here.
yes, because I think because we already answered this question, because the interaction energy is not the right energy we should be looking at here, right? We know that we should be looking at the Gibbs free energy. Okay. Right, so I'm using the slides because I didn't expect that, we already reached to the Gibbs free energy in the previous slide, so that I designed this, but it's contribute to our understanding. So because the interaction energy, as we typically understand, right, because when we talk about energy of the system, typically we talk about this interaction energy. The point I'm making here is that in order to determine the thermodynamic state or the stable state of the system, we should not look at the so-called interaction energy alone. We should look at a broader, energy functional that incorporates the different microstates or the randomness of the system as well. Okay, and this randomness is actually rigorously introduced through entropy, which we'll discuss on Thursday, and is coupled with temperature. Okay, so in the form of a Gibbs free energy, you definitely have contribution from this interaction energy, but also you have a contribution from the entropy that quantify the randomness of the system. And we know randomness is favored at high temperature, okay? And interaction energy is favored at lower temperature. Okay, so this basically rationale why transformation occurred, right? We know the Gibbs free energy play a role, but we still, don't know exactly what the form of this energy. And here I'm trying to say, in general, this free energy will contain two contributions. One from the interaction energy, okay, which is more favored at a lower temperature. The other one comes from the randomness of the system, which is entropy, which is more favored at a high temperature, right? And with this understanding, we don't have to show the mathematical form of the free energy, but with this understanding, knowing that it has two contributions, it has two components, one favored at lower temperature, one favored at higher temperature, we can already rationale why we see the transformation occur. Does this make sense? Because water have this random microstructure, which is favored by higher entropy at higher temperature. So water is the more stable state at higher temperature, right? because in the free energy, it has two components, has this interaction energy component and this entropy component. Water has this higher entropy, which is favored at higher temperature. So water is the stable phase we see at higher temperature, right? And on the other hand, the solid has a lower, interaction energy, which is favored at a lower temperature, right? So that's why we see solid as the stable phase at the lower temperature. So I'm just using this qualitative picture to try to rationale answer the question why it occurred, why the transformation occurred. Okay, but since we already got to the free energy in the previous slide, so this is just like a recap. Does this make sense for everyone? Okay, so again, this is a qualitative understanding of why the transformation occurred. Okay, so now how it occurs. Again, we already reached this a little bit in the previous slides, but now I'm showing these cool animations. So you may, this hopefully going to help us better understand. So this shows you this animation. I didn't make them, so I have to give the credit to the guy who made this guy. This shows the nucleation processes, but it's not for water, but it's for a monatomic system like liquid argon. Okay. So basically, you can understand that these individual spheres are individual molecules or atoms of the system, and this big guy is a stable nucleus. Okay, that is probably going to grow, but this animation didn't show that. And in here, you see a fluctuating nucleus, which is more closer to the screen. Okay, so it appears to be larger, the atoms. So it's fluctuating in the sense that it's not always growing. I think it grows a little bit, and then some of the atoms are deassociated with it. Okay, so I think this animation vividly showed us, the nucleation processes. What happens, how it happens, and also understand the fluctuation. Right, a nucleus will always form in the system, but in the liquid, a solid nucleus will not be stable. It will form and melt back again. Only when the temperature is lower than the melting point, so that these nucleus in the solid structure are stable. Only at this condition, they can further grow by adding more atoms to the surface. Okay, does this make sense to everyone? But once we have the nucleation, okay, which is basically determined by the fluctuations, when more atoms are adding to this nucleus, we're going to observe this growth processes. Again, this is not my image. I took it from the web. And I think this illustrates the beautiful, the growth of the ice crystal. Okay, so I think it already shows you some anisotropy, but this is maybe inherent from the internal structure. But you can see the growth, right? You cannot see the individual water molecules added to this, but you can see basically the elongation and propagation of what we call the solidification front. Okay, and eventually this is going to crystallize into I think a snowflake probably. But this illustrates vividly the growth processes. Okay, and in the real material, in the solid material, eventually if we have this water in the glass, these nucleation and growth processes will occur probably starting from the boundaries, because that's the place you have lower energy or more defects for you to nucleate more easily, and then start to grow from there and until all of the liquid phase that convert into the solid phase. Okay, so yes, sure.
Here, are these microscopic fluctuations the same as the metastable states? Are they one and the same, or?
I would not say it's a metastable state, because these thermodynamics, the nature of thermodynamic of fluctuations and metastable state, I think, are the same. The difference is that we typically do not call these fluctuations a state for two reasons. Number one, they're too small. They're only on atomic level. Typically, when you talk about states, it refers to a macroscopic thing, right? And these are very small. These are only a few, probably nanometer, or even smaller, just a few astrom. And secondly, is that they're so the time of existence is so small, it's so short. They only can exist for probably less than a millionth of a second, or even less than that. And when you say a metastable state, it lists something that you can observe on a macroscopic level, right? So typically we do not call them a metastable state. Okay, a metastable state is ice, a melting ice, right, at a temperature higher than 0 degrees Celsius. Okay, we know that ice is not stable at this higher temperature. We're observing it's melting, but you still see ice, right? So that is a metastable state. But in here, it's more like, just a microscopic fluctuations. Does that make sense?
Thank you, Professor.
Yeah. But they're atomic wise, they're the same thing. It's just the scale and the length and time scale of their existence are quite different. So that's makes the distinction. Okay. Any other questions? Okay, if not, let's move on. So that is the simple liquid solid transformation, right? And of a very simple single component system, just for liquid water, right? We have only H2O, which is a very simple molecule. But in real materials, we're gonna deal with first multiple component system. Most engineering materials that we're dealing with are alloys, which means that these systems are composed of more than one elements. You alloy them together, right, to make better material. So, and as you can imagine, the microstructure of the system will be much more complex than the liquid water. And the reason is that in the water, in the example of water and ice, we only worry about these atomic level microstructure, right? As I show here. So this is the system of a lead-tin alloy, which has been extensively used as solder material in almost all electronic devices. I think even in our cell phone now, if you open up, you see a lot of these solder joints, okay? And their mechanical properties are very important, right? I think we can see that because, you don't want, we don't want this to happen, but occasionally we drop our phone on the table or on the floor. And when you drop the phone, it will actually, undergoes a huge impact force, right? Your screen gonna crack, but the electronic devices, the chips inside the phone also feel this impact forces, and you didn't want the joint to be broken under this impact force. Otherwise, the whole thing gonna be, gonna work. But anyway, so we want the solder material to be highly conductive, but also to be very stable or mechanical or resistance to this impact forces. So we have to do quite a good engineer of the microstructure to achieve this, right? And this is just for the lead-tin alloy. And for other engineered alloys like aluminum alloy, magnesium alloy, and even for steel, there are a lot of applications that require us to carefully engineer the microstructure, which we have to understand, what are the transformations are occurring during the processing. So that's why we have this class again. But the point here I'm making is that, if you look at alloy, this is a phase diagram, similar to the one that I show you for the ice and water. But in this case, you'll see that the axes we're dealing with are different, right? So the horizontal axis is not temperature, it's the percentage or the composition, which amount of each element you're putting in this alloy. And the vertical axis is temperature, okay? Now in this phase diagram, you didn't see pressure. Why is that? Because we do not typically control pressure in processing this alloy, right? We just use atmosphere pressure, and what we control are the temperature and also the composition of the alloy, right? We can add different amount of A and B or vice versa, and we can cool the system at different temperature with different cooling rates. So those what we can control. So that's why we make the phase diagram for the alloy only considering these two control parameters, temperature and percentage of one of the elements. Does this make sense, everyone? Okay, another thing that we have to worry about is that, like in the water example, we only need to worry about atomic structure, right? Which I show as the schematic plot here. Okay, can you see my mouse here? Okay, I show the three type of microstructure. Okay, now what this microstructure corresponds to? What do you think? So let me ask this. Okay, have you seen this phase diagram before or seen similar phase diagram before?
Yes.
Yeah.
Okay, so we know how to read the phase diagram like this, right?
Yeah.
Yes.
Okay, so how many phases do you think we have here?
2.
3. Alpha, beta, and liquid.
Okay,
Yeah,
so let me
three
make it.
phases.
So there's 3 single phase regions we see here, right? Alpha, liquid, and beta. Okay, and liquid is liquid. So this is very straightforward. And alpha and beta, there are 2 different solid phases, right? Okay, now if I ask you, okay, I already give you this plot here. So if I ask you, okay, what do you think are the differences of the 2 solid phases? We talk about definition of phase, right?
Yeah, the structure is different. The crystal structure is different.
Composition also.
the
Means
composition
FCC
is
and
different.
other is BCC.
Exactly. The composition is different and the structure is different, right? Does it make sense to everyone? So the alpha phase is what we call the lead-rich phase, okay? And the beta phase, as you can see, the composition is the tin-rich phase. Okay, does it make sense to everyone?
Mm.
Okay, now based on this, I'm going to ask you, okay, which particle, so I have two particles of two different colors, blue and white. Okay, which color indicates the lead particle and which color indicates the tin particle?
Dark is lead.
Blue is
The blue is lead, right? Because we know that in this case, the blue, this is a lead rich and we have more blue here, and this is tin rich and we have more white here or empty here, right? So the blue represents the lead and the white represents the tin, right? That's very, very good. Okay, so but you see that you have to always go back and forth, making connections to all this information together and make them consistent. Okay, and so these two phases are distinguished by both the microstructure, because here you have FCC, here you have BCC, and their composition, because this is lead rich, this is tin rich. I'm sorry, this is not really BCC. This is body center tetragonal, but it's similar to BCC. Yeah, this is tin rich. Okay. And this is liquid. But more importantly, not only like in this alloy, we talk about their atomic level microstructure, we have these regions. We have these regions and these regions, okay? What do we call these?
That's
Solid solutions.
We call them solid, not necessary solid solutions. In certain cases, they are solid solutions, but they may have different type of phases, okay? We call these two-phase regions on the phase diagram, okay? So this is liquid alpha coexistence region. This is liquid plus beta coexistence. This is alpha plus beta coexistence. Okay. So now let me ask you this question. Okay. So in this alloy, these coexistence are regions. They have certain area in the phase diagram. Do we have a coexistence in pure system to single component system like the water?
yeah.
We do have coexistence, right? Because we observe water and ice can coexist at 0 degree, right? Solstice. So they do exist. But what if in the phase diagram, do we have a region of coexistence or just a line?
we can have both, right? We have those 3 points where all those three phases can coexist.
Yes.
Yeah,
the purpose of the question is to distinguish coexistence of an alloy system and a pure system. Okay, system of a single component. For a single component, you do not see these coexistence as regions. Okay, you see them as a single line. Okay, because in here, the reason why you see them as regions is because you have additional degree freedom of composition. Okay, we're going to touch that later, but I just want to point out this difference. But the key thing I'm making here is that because of this additional degree of freedom, you can control the microstructure in a much broader way. Like in the ice and water, you either have ice or water on atomic level, right? There's no much you can, basically play with the microstructure. But in here, because you have two-phase coexistence and you have this two solid phase coexist, you can have a microstructure of this, okay? Now, this is not a solid solution, okay? This is the two separate phase that occur simultaneously in the system, because the red phase, the dark one is the lead rich, and the white one is the tin rich. So the dark one is the alpha phase, and the white one is beta phase. You have two phase coexist in the system, so it's not a solid solution. Okay, but through this, we're going to talk about all the details later. So don't worry about if it's not quite a good understanding here. Okay, so we can control the amount of each phase, and by controlling the processing pathway, we can even control, the pattern of these stripes. All of this is going to play an important role in the mechanical properties of the system. Okay. So I think I'm running out of time. Okay, so that's basically all I want to tell you for the first lecture. We give an overview of the topic of this class, and the two key questions is to understand why a phase transformation occurs and how it occurs, and respectively through thermodynamics and kinetics. Okay, so I want to quickly go through the topics which are already listed in the syllabus. So, based on, these two questions, so we're going to spend a few lectures in the beginning to talk about thermodynamics, and then the rest of lectures will be on kinetics and diffusion. And these are the two important tools we're going to be using, okay, for understanding all of the subsequent phase transformation systems, right? And once we understand these two, we can apply them to different type of phase transformations. The first one is gonna be liquid solid transformation, like in the water ice example. And then we're gonna go on to talk about solid transformation, alloy solidification, and eventually solid to solid transformation of different types, including precipitation growth, spinel decomposition, eutectoid, and eventually we're going to talk about some diffusionless transformation, okay, which occur with different mechanisms, do not occur through nucleation and growth, okay? And during this processes, we're going to have 5 homework assignments. Basically after each topic, after each group of topic, I'm going to give you assignment to work on, which to reinforce what we discussed in the class. And we're going to have 2 exams, 1 midterm exams scheduled at March the 4th, and the final exam, and the schedule is to be determined. That's pretty much all I have for today's lecture. And here are some of the topics which I feel very challenging. I wouldn't go through them for the sake of time, but eventually, I just give this list so that if you're familiar with some of the topics, it's good. If not, those are the topics that you should pay more attention to during the subsequent lectures. But all of this already posted, so you can review them. And let me know if you have any questions. So yes, that's all I want to say for this lecture. Any questions?
I have a question, Professor. Will
Sure.
this course be offered on Zoom itself throughout the semester?
I'm sorry, could you repeat that?
Will this course be on Zoom itself throughout the semester, or at any point will we be having classes in the ECG building?
For now, I plan to have it for Zoom for right now, but it all depends on how the situation evolves. If we all get vaccine at some point, or everything's under control, we may switch this to in-person mode. But for now, I plan to have Zoom.
Thank you.
Yeah. Yes. Also, we will host office hours on Tuesday and Thursday from 2 to 3 p.m. But I will highly appreciate if you want to go to the office hours and have questions, please send me a note beforehand so I can arrange the times. So in this way, because we're doing the Zoom meeting, it's not like you just walk in the office. So there are possibly multiple questions from different students. So if you send me a note, I can arrange the time so that we can make the best use of this office hour time. Okay. Okay. So if no more questions, that's all.
Professor,
Yes.
I have a really quick question. The exams, are they going to be on RP now?
I'd have to work it out. I don't have a clear plan for what exam looks like. I may consider to have take-home exams because given the nature of how the lectures are delivered and the depth of the topic, but I'm not quite sure now. I have to discuss with my chair to see what is the best option, but I will let you know as soon as I know what the best way to give the exams.
Okay, thank you.
Okay. Okay, so thank you again for your time and for this lecture. Again, if this is the first time I do this online version of the lecture, so any feedbacks and suggestions on how to improve is highly appreciated and very welcome. You can just send me emails or reach me out during the office hours. Okay, so that's all for today. Again, thank you so much for your time, and I will see you on Thursday. Thank you.
Thank you.
Thank you.